In a previous video, we talked about the pHs of strong acids and strong bases. Now we're going to talk about weak acids and bases. The difference between strong acids and weak acids is that weak acids reach a dynamic equilibrium with hydrogen ions and the conjugate bases that they have. So, by contrast, a strong acid like HCl completely, one-way arrow, breaks up into H plus and A minus. But a weak acid is going to reach dynamic equilibrium with H plus and its anion, B minus. So we have a double-headed arrow there. It's a reversible reaction. Example, HI completely dissociates to H plus and I minus, but HF is a weak acid, and it does not completely dissociate into H plus and F minus. Of course, in reality, that's just a model. Really what's happening is the HI and the HF are both reacting with water to produce hydronium ion. Like all equilibria, when you reach dynamic equilibrium, there's this constant that we know about. It's the Kc, but we give it a special name, Ka, for a weak acid. And in the denominator, you're going to have the concentration of Ha at equilibrium. And in the numerator, you're going to have the concentrations of H plus ion and A minus ion. Or if you think about it with the water becomes hydronium model, it's H3O plus concentration times A minus concentration over HA concentration. Very equivalent. You can use these things interchangeably. H plus just basically means H3O plus concentration. So that Ka is called the acid ionization constant, or it's sometimes called the acid dissociation constant, but usually people just say Ka because it's quicker to say. The meaning of a Ka value is relatively how much H plus ion is going to be present when you reach equilibrium. The bigger Ka is, the stronger the acid is. So thinking about these two in comparison, 10 to the minus fourth is a way bigger number than 10 to the minus 10th. So of these two acids, HNO2 is going to produce more H plus ions at equilibrium than HCN. In other words, it's a stronger acid. They're both weak acids. They're not absolutely strong like the 6 strong acids, but HNO2 is stronger than HCN based on these numbers. How can we find the pH of a weak acid? Let's use an example here. HNO2, we know its Ka value. We want to know the pH of a 0.1 molar solution of it. Okay, so how we're going to set this up is with a rice chart. HNO2 aqueous is going to ionize to H plus, I'm using that model, and NO2 minus in aqueous solution. Initially, we had a 0.10 molar solution. Before it ionizes, you have no H plus and no NO2 minus. The change is going to be minus X plus X plus X. At equilibrium, this is going to be 0.10 minus X and X and X. So Ka, which remember is going to be H plus concentration times NO2 minus concentration divided by HNO2 concentration. In our chart, that's going to be X times X on the top and 0.10 minus X on the bottom, and Ka is 4 times 10 to the negative fourth. Then you may be able to simplify by eliminating the X on the denominator, or not. You can just solve the quadratic. It's pretty easy to do. Whatever strategy you use, you should come up with X being equal to 0.0061 molar. And because that's the concentration of H plus, that's going to help us get towards pH, because pH is the negative of the base 10 logarithm of that concentration, and so that comes out to 2.21. This is kind of the opposite problem. We have a 0.2 molar solution of a weak acid, and it has a pH of 4.07, and we want to know what is Ka. So to find what Ka is, we're going to have to find out what's the H plus concentration and what's the A minus concentration for this weak acid divided by the concentration of HA. Let's set up a rice chart for this generic acid, HA, in equilibrium with H plus and A minus. Initial concentration, 0.200 molar. These are both zeros. The change, it's all one-to-one stoichiometry. At equilibrium, this is going to be 0.200 minus X. This will be X and this will be X. Ka is going to be X squared over 0.200 minus x. Now, if we knew what x was, we could evaluate Ka. And in fact, we do, because x is the equilibrium concentration of H+, which is going to be equal to 10 to the minus pH, as we saw in the previous video. So in this case, 10 to the negative 4.07, which comes out to 8.5 times 10 to the negative 5. So Ka for this acid is equal to 8.5 times 10 to the negative 5 squared divided by 0.200 minus 8.5 times 10 to the negative 5. And you can probably just ignore that because that's very small compared with 0.2, or not. It's pretty easy to do the math either way. You come out with 4.3 times 10 to the negative 4 for your Ka value. Here's another problem to solve. What's the percent ionization of a 0.2 molar solution of acetic acid? And Ka is given. So let's set up a Rice chart. HC2H3O2 is going to be in equilibrium with H plus, and C2H3O2 1 minus. Initial, it's a 0.200 molar solution. Change, it's all 1 to 1. Equilibrium, this will be 0.200 minus x, this will be x, and this will be x. So Ka, which is 1.8 times 10 to the negative 5, is equal to, in the numerator, H plus concentration times C2H3O2 1 minus concentration, which is just x times x. In the denominator, 0.200 minus x. 10 to the minus 5 is pretty small, so I'm going to say 1.8 times 10 to the negative 5 is equal to approximately x squared over 0.200. To make my math simpler, you don't have to. You can solve the quadratic if you feel like it. And x ends up being 0.00189. That is, among other things, concentration of H+, but another thing that it means is how much acetic acid ionized. So if I want the percent that ionized, I'm going to take that amount, 0.00189, and divide it by the initial amount, 0.200, and then express it as a percent by multiplying by 100, and I come up with 0.94%, so not very much of it ionized. Let's think about mixtures of weak acids. If I have a mixture of HCN and HNO2, what are the major species that are present in this mixture? Well, they're both aqueous solutions, so H2O is going to be the dominant species. There's going to be more of that than anything else. And then both these species are going to ionize. So HNO2 is going to reach equilibrium with H plus and NO2 minus, and HCN is going to reach equilibrium with H plus and CN minus. But those are both weak acids. 10 to the minus 10 and 10 to the minus 4 are both pretty small. So there's going to be quite a bit of HNO2 still left in solution, and there's going to be also quite a bit of HCN left. And probably a little bit more of HCN than HNO2 because HCN is a weaker acid, so it won't produce as much product. What else is going to be present? There's going to be a little bit of H plus, and there's going to be a little bit of NO2 minus and CN minus, but those are not the major species present. What if we wanted to know what the pH of this mixture was? Well, because HCN is a much weaker acid, about 1,000,000 times weaker, that means most of the H plus is going to come from HNO2. And before, we found out that a 0.1 molar solution of HNO2 is going to produce a pH of 2.21. So that's going to be the case here as well. The HCN is just not going to produce enough H plus to even make a difference in that value. Next question, what is the concentration of CN at equilibrium? Well, the H plus concentration is 10 to the minus 2.21, which was 0.0062. That's how we got that 2.21 value originally. So that means that Ka for HCN, which is 6.2 times 10 to the negative 10th, is going to be equal to 0.0062 times concentration of CN minus divided by the concentration of HCN, which was 1.00 molar. And that's not going to be at equilibrium very much different than 1 molar. So I'm not going to bother with the minus X part. That would have arisen if we had done a Rice chart. So because that's 1, it just cancels out, and then we can just solve this for CN minus, and the concentration of CN minus comes out to be 1 times 10 to the negative 7th. Weak bases. Weak bases, like weak acids, reach a dynamic equilibrium with hydroxide ions and the conjugate acids. So here's the general formula for a weak base. B is the base. It reacts with water. Reversible reaction forms an equilibrium with a conjugate acid, Hb plus. Notice that it's one more H, one more plus hydroxide ion. Here's an example. Ammonia, kind of a classic weak base, reacts with water to produce ammonium and hydroxide. Of course, because it's an equilibrium, there's an equilibrium constant. We call it Kb for base, and it's Hb plus concentration times OH minus concentration in the top, and B concentration in the denominator. Water does not show up because it's a liquid. Kb has a name. It's called the base ionization constant or the base dissociation constant. But again, just like Ka, we usually just say Kb because it's quicker to say. There's a ranking that you can get from Kb, just like from Ka. A bigger Kb means there's more hydroxide ions at equilibrium, so we would say that that's a stronger base. So if we're comparing these two bases, NH3 and CH3NH2, looking at the values of Kb, that's a bigger number than that. So that means CH3NH2 is the stronger base. We can solve problems in a very similar way with bases and acids. So here we have C2H5NH2, which has a Kb of 5.6 times 10 to the minus 4. And our objective is to find out what's the pH of this solution. Let's set up a Rice chart. C2H5NH2 is going to react with water. It's going to produce a conjugate acid, C2H5NH3 plus. Add an H, add a plus, and hydroxide ion. Initially, this is a 0.1 molar solution. Water's a liquid, we don't care about it. No products before the change. During the change, we're going to lose X, gain X on the product side. Everything's 1 to 1. At equilibrium, this is 0.10 minus X. This is X, and this is X. So Kb, 5.6 times 10 to the negative 4th, is going to be conjugate acid concentration, which is X, times OH minus concentration, which is also X, divided by 0.10 minus X. Then solve this whatever way you want to, and X turns out to be 0.0072, and what that is equilibrium concentration of OH minus concentration, among other things. So that means POH is negative base 10 logarithm of 0.0072, which is 2.14. But we want pH, not POH. So the pH is going to be 14 minus 2.14, which comes out to 11.86. Here's another problem. The pH of a 0.2 molar solution of some weak base is 10.92. What's Kb? So if we set up a Rice chart for our generic weak base B, reacting with water, reaching equilibrium with its conjugate acid, Hb plus, and OH minus. The initial concentration was 0.200. These are going to be zeros, minus X and plus X's, 1-to-1 stoichiometry. At equilibrium, this is 0.200 minus X. This is going to be X, and this is going to be X. So Kb, which is what we're trying to find, is going to be X squared over 0.200 minus X. So what is X? Well, X is hydroxide ion concentration at equilibrium. We know that the pH is 10.92, so that means that POH is 14 minus 10.92, which is 3.08. So that means the OH minus concentration is 10 to the minus 3.08, which is 8.3 times 10 to the negative fourths. So that is what x is in this equation. So our Kb value is 8.3 times 10 to the negative fourth squared divided by 0.200 minus 8.3 times 10 to the negative fourth. And that comes out to a Kb of 3.5 times 10 to the negative sixth for this base. Let's relate Ka and Kb for a conjugate acid-base pair. For the acid, Ha, in equilibrium with its products, K is Ka for that acid. If we have the conjugate base of Ha, that's A minus, reacting with water to produce Ha and OH minus, that K is the Kb for the base. If we sum these together, Ha cancels out, A minus cancels out, and we just end up with the autoionization of water. And K for that is Kw. So Kw is the Ka for the acid times the Kb for the base. So that's how they're related to each other. Remember, Kw is 1.0 times 10 to the negative 14th. For example, if we wanted to find out what Kb was for NO2 minus, if Ka for its conjugate acid, HNO2, is 4 times 10 to the minus 4, we could do this by taking that equation and solving it for Kb. Kb is going to be Kw divided by the Ka for the conjugate. So Kb for NO2 is Kw divided by Ka for HNO2. So that's 1 times 10 to the negative 14th divided by 4 times 10 to the negative fourth, which comes out to 2.5 times 10 to the negative 11. One more example problem. What if we wanted to know the pH of a 0.2 molar solution of sodium acetate? We are given the Ka for acetic acid. Notice that acetic acid is the conjugate acid of the anion in sodium acetate. So what's going to happen is when this dissolves, it's going to produce sodium ions, which don't have any effect on anything, but it's also going to produce C2H3O2 which is a base. So let's set up a rice chart. C2H3O2 is going to react with the water that's in the solution and produce HC2H3O2, the conjugate acid, and some hydroxide ion. And how much hydroxide ion is in there is going to be what influences the pH. Okay, initially, this was a 0.20 molar solution because this is one-to-one stoichiometry. 1 mole of this makes 1 mole of this and also 1 mole of this. So the concentrations are the same. So that's 0.200. Don't care about water. These are both zeros. One-to-one stoichiometry, which is often the case, makes this pretty easy. This ends up being 0.200 minus x. This is x, this is x. So Kb is x squared over 0.200 minus x. And if we can figure out what x is, that's the concentration of OH minus, and then we can get our pH from that. So what's Kb? Well, our Kb is going to be 1 times 10 to the negative 14th, that's Kw, divided by the Ka for the acid, which is given to us as 1.8 times 10 to the negative 5. This ends up being 5.6 times 10 to the negative 10. So 5.6 times 10 to the negative 10 is equal to x squared over 0.200, and I'm going to leave off the x because 10 to the minus 10 is very small. And then we can solve for x, and we find out that x is 1.1 times 10 to the negative 5, and that is the concentration of OH minus. So that means POH is equal to negative base 10 logarithm of 1.1 times 10 to the minus 5, which is 4.96. So that means the pH is 14 minus 4.96, which is 9.04.